So you probably just finished up the Mythbusters video where they looked at the legend of if you drop a penny from the observation deck of the Empire State Building, it will have enough velocity that when it reaches the ground, it's capable of killing somebody. And so ultimately what they found was that that myth or that legend is a myth. It's not true. And so what they did was they applied physics to determine whether or not that hypothesis was valid or not. And so this was a nice problem to show where physics can be applied and is applied on TV and around us. And it's also a good problem because it's something that you'll be able to do by the end of this module. So we're not going to go ahead and solve this because it's actually something that you're going to be doing. The physics side of what the Mythbusters team did was they needed to determine what the velocity was, what the velocity is at the street level. And so to determine what the velocity is, you need to use the kinematics equations. And so these kinematics equations in one dimension describe the motion of an object. And so this builds off of the ideas that we looked at in Module 1. And these kinematics equations are valid for constant acceleration. So if their acceleration is not changing, then these kinematics equations are valid. The one-dimensional aspect of it is these apply for motion in the x direction, so more motion horizontally. It can also be applied to motion entirely vertical, like a penny being dropped down. It's just going to change what these labels are. So horizontal motion will be x, and for vertical motion, it will be y. All you need to do is just replace where there's an x with a y. So this equation here will just be Vy is equal to V naught y equal to A, or excuse me, plus AY T. So it just changes what that subscript is to tell you motion in the x direction or motion in the y direction. Either case is still just one-dimensional motion. If you're just moving horizontally, it's one dimension, the x direction. If you're just moving up and down vertically, then that's just motion in the y direction. So looking at these equations, if you haven't seen them before, it probably looks pretty daunting. There's a lot going on. There's squares. There's a lot of terms. So what we're going to do is we're going to walk through these and just talk about them just using words. So this first equation here, this should look familiar from Module 1. This is just the average velocity. The change in position over the change in time is just the average velocity. Now we look at the average velocity can also be the velocity at the start or the initial instantaneous velocity. So it's the velocity at that particular moment. That's what instantaneous means. And then this is the final instantaneous velocity. And that's divided by 2, and that's equal to the average velocity as well. So if you know the velocity at the start and the velocity at the finish, you can determine what the average velocity is. This is very similar to just taking the mean of something. You know something at one point and you know something at another point. You add those two together and divide by 2, you get an average between those 2 points. The second equation we have here is position as a function of time. So we have our final velocity, or final position, excuse me, is equal to our initial position plus how much we move in between those 2 points. So we're starting here, we move some amount, which is this part, and then we get to our final position. The next equation is just velocity as a function of time. And so this should look familiar from the previous module where we described what acceleration is. So acceleration is just the change in velocity over the change in time. But that's just equal to velocity final minus velocity initial all over the change in time. And so you can rearrange this to get this equation. You just need to multiply by time and then add over the initial velocity. And then you get this equation. So it's just a reworking of what we saw in Module 1. And then the last equation is velocity as a function of position. So there's no time in this equation. So in problems where you're not given any information about time, this can be a useful equation to apply. And so it's actually something that you can use to solve this problem. If you know the height of the building, which is the change in position, and you know that you're starting from rest, you're just dropping the penny from your hand, all you need is information about the acceleration of the penny in the air to be able to solve for the velocity at the ground. And so this is something that you're going to get practice with, choosing which equation for a physical situation. And it's actually something that you're going to solve in terms of finding what the speed of the penny is at the bottom of the ground using these kinematics equations.